Okay, and so this was the Thursday one for April 1st. Here's our Lorentz series again. Residue is that term, that coefficient, integral around a curve, blah, blah, blah. Gamma is simple closed, positively oriented curve entirely within A0, is 2 pi I b1. An isolated singular point is a function. For a function is a point z0 where f of z is analytic in the punctured disk. So an isolated singular point, basically when you're dividing by 0 is the classic example, right? I have a punctured disk. The function is analytic everywhere but there. And there are 3 types of isolated singular points. A removable singularity has all of these b sub i's equal to 0. A pole has a finite number of these not equal to 0. And then a essential singularity has infinitely many of them not equal to 0. So removable singularity, how do we find the Lorentz series for sine z over z? Sine z over z is 1 over z times z minus z cubed over 3 factorial plus z to the 5th over 5 factorial minus dot, 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 keeps going on. And so if we divide everything by z, we get this. Oh, this is z squared plus z to the 4th over 5 factorial, right? And note, not defined at z equals 0. Okay, so what's the limit as z goes to 0 of this function? Well, that's why Taylor series are so useful. All right, if you remember back in calculus, we had to have a complicated way to figure out what that is. We had to do that because we needed to be able to define Taylor series, but once you have a Taylor series, you can calculate the limit easily enough. And it's just 1. So if we make this w equal to 1, or z equals 0, then that gives me a function that's analytic everywhere, right? Because it's we now have defined what it should be at z equals 0 to make this function analytic. And what's the Taylor series for g of z? It's 1 minus z squared over 3 factorial plus z to the 4th over 5 factorial minus dot, dot, dot. Remember that this is technically for z not equal to 0 because the original function wasn't defined there. So a removable singularity means that you can remove the singularity by finding the limit and then putting in the appropriate number. So a pole is degree m means that bm is not equal to 0, but bk is equal to 0. So what that means is that our Lorentz series will be bm over z minus z naught to the m plus bm minus 1 z minus z naught to the m minus 1 plus dot, 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 plus b1 over z minus z naught plus a0 plus more stuff, but nothing here, right? This is the z0, the m is the biggest negative power that you get. And remember that this is the definition of what the coefficients in a Taylor series is. So if f of z has a pole of degree 3 at a point z0, then its Lorentz series is b3 over, let me rewrite that so it's a little clearer. Plus blah, blah, blah. So that's the series that we get. It's a pole of degree 3, so we don't have a degree 4 or degree 5, etc. for this. So g of z equal to z minus z cubed times f of z. Well, g of z is b3 plus b2 z minus z0 squared plus, oh, not squared, plus B1 times Z minus Z0 squared plus A0 times Z minus Z0 cubed plus A1 times Z minus Z0 to the fourth plus blah, blah, blah. So we took this function, we just multiplied it by Z minus Z0 cubed. That canceled out this. B2 now is Z minus Z0. So what do we have? We have a series where you have no terms with negative powers. And that is a removable singularity, because that's the definition of what it means to be a removable singularity. Great. So, and that gives us the Taylor series for G of Z. And that's above. And so B1 is the coefficient of the Z minus Z0 squared term in G of Z. So if we know what G of Z is, if we know the function G of Z, then we know that B1 is 1 over 2 factorial times G2 of Z0. And remember that when we put something inside parentheses like that as a superscript, that means second derivative. So that tells you what B1 is in terms of G, right? Because B1 is the coefficient of Z squared, and the coefficient of the Z squared term is the second derivative divided by 2 factorial of whatever function you're dealing with. Great, so here, h of Z is some function. We know that cosine Z over Z cubed is a function, and what's the Lorentz series for this going to be? It's going to be 1 over Z cubed times 1 minus Z squared over 2 factorial plus Z to the fourth over 4 factorial, right? The usual Taylor series for cosine. That should be minus, dot, dot, dot. And so that'll be 1 over Z cubed minus 1 over 2 factorial, 1 over Z, plus Z 1 over 4 factorial, Z squared, minus dot, dot, dot. Okay. So the residue is the coefficient of that term. Residue of h at 0 equals minus 1 over 2 factorial. Okay. My formula from 5 is B1, which is my residue, should be 1 over 2 factorial times the second derivative of my function g at z0. And what's g of z here? Well, I take my function and I multiply it by the power that's in the denominator, and that gives me g of z. And in this case, that's cosine of z. It's the numerator. So second derivative of cosine of z is minus cosine of z. We're centered at z equals 0, so minus cosine of 0 is minus 1. So the second derivative of g evaluated at z0 is actually minus 1, and so we get b1 equals minus 1 over 2 factorial, which is the same thing we got there. Okay, so generalize this process to get a nice formula for finding a residue for functions that look like this. Okay, so f of z is some function and it has Lorentz series, right? And it's going to start with bm over z minus z naught to the m plus lots of terms plus b1 over z minus z naught plus a0 plus a1 z minus z naught plus lots of terms. So g of z is z minus z naught to the m times f of z, right? This is our numerator. And that's going to be, well, if I multiply by m, that'll be bm plus dot, 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 plus, now if I multiply this term by z minus z naught to the m, that will give me a b1 times z minus z naught to the m minus 1, and then plus a0 z minus z naught to the m plus dot, dot, dot. So g of z has a removable singularity. And so we can just consider it as being analytic in the analytic in a disk centered around z0, or an analyst centered around 0, actually in the disk, right? So g of z is a removable singularity. You remove the singularity, you get a function that's analytic in the disk around z0. So b1 is, this is a Taylor series for g centered at z minus z naught. And so b1 is the coefficient of the m minus 1 term. So b1 is the mth derivative at z0, m minus 1th derivative, sorry about that. M minus 1th derivative at z0 of over m minus 1 factorial. And that's our residue. And that's very nice, because it gives us a very nice formula for dealing with functions that are of this form, because then we can find the residue very quickly. And that's nice because of looking at this problem, right? Finding the Lorentz series for this is kind of a hassle. You have to rewrite the top in terms of powers of z minus 1 and then divide and blah, blah, blah. But the residue should be from our formula above, g m minus 1 at z0 over m minus 1 factorial. That's just this formula rewritten in a totally illegible scribble, it looks like. So what is the function g of z here? G of z is z to the 5th plus z cubed plus 1. And m is equal to 4, because we have a polar of order 4. So that means we need the third derivative of this. So the first derivative is 5z to the 4th plus 3z squared. The second derivative is 20z to the cubed plus 6z, and then the third derivative is 60z squared plus 6. The center is z equals 1, so g third derivative at 1 is 66, because you just plug 1 in here. And then 3 factorial, so b1 equals 66 over 3 factorial, and 3 factorial 6. So it's 11. So not too bad. Singularities. Essential singularities are really weird things. So f of z equals e to the 1 over z. Right? It's going to be that. Right? You take the series for the exponential function and you just plug in 1 over z for z and you get this. So infinitely many, in fact all, we actually have infinitely many terms of that form, so it's an essential singularity. And you can think of e to the z as a composition of functions. Right? Z goes to 1 over z to e to the 1 over z. So if we think about mapping properties of e to the z, we remember that e to the z maps any vertical strip, solid here, of height 2 pi. It'll map that onto the entire plane except for 0. So that's what e to the z does. So if we have a ball of radius r centered at the origin, right, no matter how big this radius is, I can always find a strip up here of vertical height 2 pi that's not inside the ball at all. So the exterior of this ball, what does e to z map that to? Well, it maps it to the entire plane because it maps every strip that looks like this to the entire plane. And so this, since this is entirely the exterior, the entire plane gets mapped. The exterior of any disk, excuse me, gets mapped to the entire plane. What does 1 over z do? So if I have an annulus of radius 1 over r, 1 over z will invert that. And so we take the interior. Things close to 0 get mapped to things close to infinity. 1 over r gets mapped to r. So that maps it to the exterior of the circle of radius r. There's an inversion in there, right? So if I take a point here, 1 over r will be outside, but it'll be down on this side because you flip the angle. The argument goes from being positive to negative. So why does e to the 1 over z map any punctured neighborhood of the origin onto the entire plane? Well, if I take any punctured neighborhood of the origin of radius, say epsilon, then 1 over z maps that to the exterior of a circle of radius epsilon. So we take the interior here, we get mapped to the exterior, and the exterior of any circle by e to the z gets mapped onto the entire plane because the exterior always has some kind of thing of radius 2 pi, which means back here somewhere there was some little annulus that got mapped to this thing, or whatever shape it is, that gets mapped to this thing, and then that gets mapped everywhere. The weird thing about this is it doesn't matter what your epsilon is, right? Whatever epsilon you pick, whatever small radius you want, you always map, even as you get smaller and smaller and smaller, you always map that region to the entire plane. So, why are these two statements the same? F of z equals e to the 1 over z maps any punctured neighborhood of the origin onto the entire plane except for 0, is saying that for any epsilon greater than 0 and any w not equal to 0, there's a solution to this equation. So I want to tie together geometry and solutions to equations. So if we want to solve the equation e to the 1 over z equals w, what that means is, you know, you'd solve it by sort of saying pick your branch of the logarithm, and then you'd say 1 over z equals log of w, where z equals 1 over log of w. And you have to be careful a little bit about defining your log branches. So no pictures involved in solving that, right? It's just sort of, I'm going to call it algebraic, but you know. But another way to look at that is to say, well, if I pick any epsilon greater than 0, right? Any punctured neighborhood gets mapped onto the entire plane, right? So W is somewhere in the entire plane, so there's something here that gets mapped to there. So if I call this Z naught, then get that. Back in algebra or calculus, right, you solve problems by looking at the graph of the function, you fix your y value, and you look for the points of intersection with the graph to solve it. This is sort of a similar thing, right? So we want to be able to think of equations as having a geometric representation, but also as having an algebraic representation. This is called the little Picard theorem, and it's true for every essential singularity. E to the z is easy. E to the 1 over z is easy because we know the mapping properties. But this statement if you replace the e to the 1 over z with a function that has a essential singularity, that's also true. So essential singularities are kind of weird things. And so there is an analogy in calculus, right? When you do limits in calculus, you come across this, and this is a removable singularity. And in calculus, you also find functions with vertical asymptotes. These are poles. And what's an essential singularity? An essential singularity that you saw in calculus, and you saw this briefly, usually we don't spend a huge amount of time on it, is the function sine 1 over x, which we have for various limits of things. And so it oscillates infinitely often as you go in towards 0. So if you think of sine of 1 over x, one of the things that it does is the range for sine of x is from -1 to 1. If I take any small interval on the real line, say minus epsilon to epsilon, what do I know about this function? Well, the function has a complete cycle in there. So for no matter what epsilon you pick, no matter how small it is, sine 1 over x covers the entire range of sine. Or there's a solution, no matter what epsilon you pick, sine 1 over x equal to y, with y between -1 and 1, always has a solution, no matter how small epsilon is, because you're oscillating up and down. And so that's an essential singularity in calculus.